everyone. So we're going to continue our discussion about momentum, and we're going to focus on something called impulse. Now, this is actually related to changing an object's momentum. So we actually mentioned before about how the more momentum an object has, the more force is required to actually change that. So when it comes to impulse is basically this measurement of how much momentum we have to change, the amount of force that we have to apply over the amount of time required. So this is an example of the difference between a kick and a shove. One is a bigger impulse than the other sometimes. So the equation for impulse is J F net T equals delta P equals M delta V. Now, a little bit about this. First, J is what we are referring to as impulse, this change in momentum. Again, it's one of those variables where it doesn't seem to really make sense with the word. Another thing that you'll notice is that this is a string equation. Basically, what's going to end up happening is you're going to read the question, you're going to figure out what exactly they're pulling out. So, are they giving you masses? Are they giving you forces, momentums, impulses? What information are they giving you? And from there, you're going to pick two of these to set equal to each other. So, if they give you impulse and mass and velocity, you're going to take the J and set it equal to this part. So, you don't have to write the whole equation. You only write the two parts that you're actually setting equal to each other. All right. Basically, it's a shorter and neater way of writing J equals F net T, J equals delta P, J equals M delta V, F net T equals delta P, F net T equals M delta V. Instead of having all those equations, we just write it as one. Another thing that you're going to notice is I highlighted this last equation in purple. The reason being is that this is not on the reference table. This is what I actually call an extension to this equation. Mainly the fact that, very similar to the centripetal force equation, where it was very commonly that you would use mv squared over r, but that wasn't on the reference table. Here it's pretty much the same idea. From the P equals mv, you can actually get that delta P equals M delta V. This is used so much that it's worth remembering. All right. And then from here, this is actually one of the reasons why I mentioned before that momentum is sometimes measured in Newton times seconds, is actually because of the fact that J being equal to F net T would have the units Newton times seconds because it's a force times time. And because impulse is related to the change in momentum, that's why they can share those units. Again, though, if you want to keep kilogram meters per second and Newton seconds for momentum and impulse respectively, that's fine. I'm just mentioning that on the regions, they're going to flip-flop according to what exactly they're referring to. All right, I don't know how many questions we can go over, but we'll start with this one. So pause the video, work yourself, and we'll go over in a second. All right, so based off what they give us the mass of 3 kilograms, they give us the impulse of 50 Newton seconds, and they want to know the change in momentum. So again, we look at the full equation. Now, I'm going to write the full equation, but from now on, you don't have to. Just look at the full equation on the reference table and pick the two. So they give me J, which I have all the information of, and the delta P. So these are the two I'm going to set equal to each other. I'm going to ignore the F net T and the M delta V. And they tell us that J is 15 Newton seconds. So change in momentum is 15 kilogram meters per second. Again, impulse is a change in momentum. So if the impulse is 15, the change in momentum is 15. The only difference is that the unit changes, but again, it doesn't have to. Here's the next question. Pause the video, work yourself, and we'll go over in a second. All right. So again, they give us a mass of 75. They give us the speed is 6 meters per second. Now they do tell us that the final speed ends up being 0. I didn't record that, but it is something else that we're told since it comes to a stop. And we know that the time is 0.65 seconds. So we're looking for the force. So again, we're looking for force. So we're going to have the F net T part. We have all the information for the M delta V. So we're going to set those two parts equal to each other. Again, very common setup. Majority, pretty much like 80% of the time, you're going to be doing F net T equals M delta V. So we plug the numbers in, we plug in the time, we plug in the mass in 0 minus 6. Because remember, delta V is a change in velocity. We're going from 6 meters per second to 0, so it's final minus initial. And I get 692 newtons. Now notice my equation, I should have gotten a negative 692. But because they say what's the magnitude, I can actually drop the negative. All right. Here's the next question. Pause the video, work itself, and we'll go over in a second. All right. So looking at this, we have mass of 0.149 kilograms. We have the velocity is 50 meters per second. Again, the final velocity is going to end up being 0 again because it says comes to rest. We know the time is 0.04 seconds, and we're looking for force. So again, using the long impulse equation, we're going to set the F net T equal to M delta V again. And then we're going to plug the numbers in. And when we chug it out, we get 55.9 newtons. Really quick, as a side note, if you actually look at this equation a little bit closer, so notice that they have F net in here. If I divide T over to the other side, I end up having the equation F net equals M delta V over T. Now, one thing that should pop out is that we have an equation for F net. F net equals MA. So if I plug F net equals MA in for the force, and I set MA equal to this M delta V, something interesting happens. We get mass on the left side, mass on the right. Those masses actually cancel out, and I get A equals delta V over T, which is my basic acceleration equation. I had mentioned before that a lot of the equations that we're going to be dealing with from now on are going to be related and brought back to Newton's second law, or Newton's three laws in general. This is one of them. So right now, this equation, this stuff that we're talking about, is actually just an extension of Newton's second law with new terminology, essentially. And one of the later videos that we're going to deal with, we're actually going to also relate Newton's third law to the whole mix as well. All right, here's the next question. Pause the video, work itself, and we'll go over in a second. All right, so based off of this, they give me the mass of 0.75. They give us the initial velocity of 0.5 and the final velocity of 2. Now, they tell me that they're both in the direction east, so I don't need to do anything crazy, but definitely keep an eye out for direction. And then from here, they want the impulse. So again, from the equation, it's very clear that I'm going to use the J and the M delta V and set them equal to each other. So plugging in my numbers, I end up getting that my impulse is negative 1.13 Newton seconds. Once again, I actually could have just dropped the negative since it tells me the magnitude, but sometimes it's nice to include that. All right, here's the next question. Pause the video, work itself, and we'll go over in a second. All right, so for here, they give us a force and a time. So they give us an initial force of 20 and a time of 10, and then they give us a second force of 50, and they want to know the time to produce the same impulse. Now there's multiple ways that we can do this. First, because of the fact that the equation is so simple, what we could do is use the force and time to find the impulse and then do that equation again, but this time changing it for the new force and solving for time. What I'm going to actually do right now is just set F net T equal to itself. So this is for case 1, and this is for case 2. So I'm going to do F net T equals F net T, which is actually perfectly fine and something that you can easily do. From here, we plug the numbers in. So in the first case, it was 20 newtons in 10 seconds. Second case, it's 50 newtons in an unknown amount of time. Solve for T, and we get 4 seconds. Now, you could also have done the 1-1-1 method if you wanted. This one was a little bit weird since you would have had to double the time, not double, but multiply it by 2.5 in order to get 50. So if you did the 1-1-1 method, you do J equals F net T. J stays the same, so that becomes a 1. the force is multiplied by 2.5. So that means my time is going to end up being 1 over 2.5. Now remember, that doesn't mean it's 1 over 2.5 seconds, but it's 1 over 2.5 times my original time of 10 seconds. So if you plug that into the calculator and you do 10 divided by 2.5, you end up getting 4 seconds. So again, multiple ways that you can do it. It's whatever floats your boat. All right, here's the next question. Pause the video, work itself, and we'll go over in a second. All right, so plugging the numbers in, we have a mass of 2 kilograms. We have an initial velocity of 4, a final velocity of 8, a time of 0.5, and they want us to find the net force. So again, we're going to set the F net T equals m delta V, basic stuff. I'll plug my numbers in. Remember, once again, we do final minus initial, and we should end up getting 16 newtons. All right, so here's the next one. Pause the video, work itself, and we'll go over in a second. All right, so plugging the numbers in, the only thing that's changing between A and this is actually supposed to be B is that the time ends up changing. So it goes from 1.5 seconds to 10 milliseconds. But they give us all the same things. They give us a mass, they give us a height, and then they give us the initial velocity, and then tell us that it comes to rest with a final velocity. And we're looking for force. So we're going to be doing the F net T equals m delta V again. In fact, the 45 meters is actually a red herring. So when we plug the numbers in for using the 1.5 seconds, we get that the force that this person's going to feel is a little bit over like 1,600 newtons, which is a fairly high force. But when we look at scenario B, where it's actually landing straight on the ground, this time with the time being 10 milliseconds, we're going to want to make sure that we convert that milliseconds into seconds. So we just plug in times 10 to the negative 3 for milliseconds. And then when we do the math, this time we get the number skyrocketing to 240,000 newtons. This is actually one of the reasons why it's not really the speed that ends up harming people when they fall. It's actually the impact time. If you're falling onto a giant pillow, because of this high amount of time, it's going to end up decreasing the force. The longer it takes for you to come to rest, the smaller the force you feel. On the other hand, if you have a very short time that you come to rest, the force you experience is going to be significantly higher. This is actually the reasons why we have airbags in cars, in order to prolong this exposure to the force. The longer the force acts on us in a case like this, then the shorter or the less that force is going to be, seeing as our impulse is going to be the same. You know, we're still going from 30 meters per second to 0. So our momentum changes the same amount. The difference is how long the force gets to apply onto us. So this is something that we have to kind of keep an eye out for. Here's the next question. Pause the video, work itself, and we'll go over in a second. All right, so we have mass, initial velocity, final velocity, and time. They want us to actually figure out not only the magnitude, but also the direction of the force. So I'm going to keep that in mind. Use my equation. Once again, F net T equals m delta V. Plug my numbers in. This time, I'm going to end up getting a negative number. So because of the fact that I get a negative, it means it's in the opposite direction of my velocities. If I look back, both of my velocities were in the direction east. So my force is going to be in the opposite direction of east, which is west. So I should end up getting 10 newtons west. Once again, note that I'm dropping the negative here because I am including direction through this. That's all the negative means in these cases. It just means direction. All right, so here's just a thought question you can think about to yourself: why we use an airbag for safety, and why do cars have these crumple zones? If you didn't know, cars were originally made very sturdy back in the day with the Model T. They could get into a huge accident with each other and not even show a dent. The big issue though was that people kept dying. They realized that the reason why people kept dying was that there was just such a high force due to the quick impact time. The fact that the car never got a chance to crumple, it just kind of stayed sturdy, meant that you felt so much more force due to the uh, extreme simultaneous impact and coming to rest. So again, going back to the equation, when we get into a collision, our impulse based off our speed doesn't really change, but what changes is the force and the time. If we have the time increased significantly, then the force we experience will be much less. So cars are actually designed to be destroyed and crumple like this so that it gives you a little bit more time to come to rest, and in order to make it so that you actually are more likely to survive the accident. So the more a car crumples, the less likely you are to be injured in an accident. It also actually works for something like this. If you've ever either got into a fight with someone or in particular played a sport where you had to catch something, like catching a baseball or catching a golf ball, if you did something like that, one of the things you know is that you don't just keep your hands and face in where they are. You tend to cradle the object. You tend to move your hands and move your face back, and all this does is actually, going back to the impulse equation, increases the time that you're in contact, decreasing the force that you're experiencing. All right, and that's pretty much it. So if you have any questions, feel free to let me know. Otherwise, I'll see you later. Good luck and have a great day.